Let's do section 2.3. The topic is properties of functions. So what we're doing in this section really is we're given the graph of a function, and that's what we use to describe or discuss these properties of functions. We're not learning too much in the way of new graphing techniques in this section. In the next section, we'll start our library of functions, and in the sections that follow, we'll have a few more techniques of graphing. But this is useful information, and a lot of this you'll see again in Calculus 1. And some of the things we'll discuss, we'll have to take them from graphs in here. In Calculus 1, you'll figure out how to do the graphs using these ideas we're talking about now. So in this section, we define even and odd functions, identify them, define increasing and decreasing functions. We will be a bit challenged to tell from the formula for a function whether it's an increasing or decreasing function, but that's one of the big things you'll do in Calculus 1. So this is very much Calculus 1 preparation, being pre-calculus and all. We'll use a graph to find local maxes and mins. Again, we're using the graph. We don't know where the graph came from. In Calculus 1, you'll prepare graphs, and then you'll do this kind of analysis. We'll use a graph to find absolute maxes and minima, and we'll find average rates of change of a function on an interval, and that you'll see again in Calculus 1. So the eye on the prize is very much calculus material. We won't do calculus material, of course, but we'll describe some of the things you're going to see again in Calculus 1. A definition. A function f is even if every number x in its domain, the number negative x is also in the domain, and f of negative x equals f of x. So an even function absorbs negative signs. For example, a squaring function would absorb a negative sign. A fourth power function would absorb a negative sign. A sixth power function would absorb a negative sign. That's the reason they're called even functions. An absolute value function would absorb negative signs. That's kind of what absolute value functions are for. So absolute value function is also an even function. So don't become too enamored with thinking in terms of even powers of the variable, as we described for x squared, x to the fourth, and x to the sixth, and so forth. Other functions can be even without those ideas. Not our problem, but in Precalculus 2, when you do trigonometry, you'll see that the cosine function is also an even function because it absorbs negative signs. And I don't see any even powers of the variable inside in a cosine function. They must be somewhere out there. This conversation to be continued in Calculus 2. For us and for Calculus 1 and Precalculus 2, even means what we just said it means. Function f is odd if for every x in its domain, negative x is also in the domain, and f of negative x equals negative f of x. I always describe this as the function spits out those negative signs. For example, if we had a cubing function, if we take negative x cubed, we get negative x cubed, trying to indicate the location of these negative signs with verbal cues. Let's do that again. Negative x cubed equals negative x cubed. Negative x to the fifth power equals negative x to the fifth power, and so forth. And that's the reason these are called odd functions. Can you think of another function that's odd other than these odd exponent ideas? Speaking of trig, the sine function is an odd function, it turns out. So even means absorbs negative signs. Odd means, if you'll give me some liberties here, means it spits out negative signs. And negative comes outside of that function if we have an odd function. It simply disappears if we have an even function. Turns out we've already discussed some things that allow us to recognize even and oddness, evenness and oddness from the graph of a function, as stated in the following theorem. And this is really just a rewording of some things we had earlier. Theorem 2.3.a says a function is even if and only if its graph is symmetric with respect to the y-axis. How did you test for symmetry with respect to the y-axis? Back when we were doing symmetry, we replaced x with negative x and tested to see if we got the same thing. Will that happen with an even function? Yeah, replace x with negative x, you'll get this. If they're the same, that is if the function is even, then that kind of symmetry holds. So it's simply a rewording of this even and oddness in terms of the symmetry that we had earlier. And if we have graphs, it's easy to look at the graph and see if we've got symmetry with respect to the y-axis. So if we have a graph, it's easy to look and see if we have an even function, the graph of an even function. Second claim is a function is odd if and only if its graph is symmetric with respect to the origin. When we had equations, we tested for that kind of symmetry by replacing y with negative y and x with negative x, I think it was, to see if we had the same kind of behavior. So what we're doing here is we're replacing x with negative x, and we get the negative of f of x. We get the negative of the y value. So there's, in some sense, there's two negations here. Replacing x with negative x, do that right there. If you replace x with negative x, that will simply produce an f of x. And if you replace y with negative y equals f of x, you would replace f of x with negative f of x. And we get this kind of equality. That was a little more complicated story on the odd functions, but I stand by the claim. It's odd if and only if symmetric with respect to the origin, and we've done loads of examples illustrating that. So we can recognize that symmetry from a graph, as well as a symmetry with respect to the y-axis. That means if we have a graph, then we can test for even and oddness using theorem 2.3.a. If we don't have a graph, well, it turns out we had some algebraic ways to test for symmetries. They were given in the definition. So we can test algebraically by testing to see if this is the case for even, or that is the case for odd. Graphically, we can look to these symmetries if we have a graph. Let's look at an example. So let's see. Let's look at number 26, I think 26 and 28, where they give us a graph. Consider the graph of f below. Okay. Find the intercepts, if any, the domain and range, whether the function is even, odd, or neither. Okay, this part A and part B stuff, that's stuff we've done before. Intercepts, well, we'll look to see where the function, say for x-intercepts, where it touches or crosses the x-axis. It touches it at this point and this point. So this point, -1, 0, and this point 1, 0. These are x-intercepts for the function. Does it touch or cross the y-axis? Yeah, it crosses it right there at the point 0, 2. So the y-intercept is 0, 2. We'll comment. You could only have one y-intercept if it's a function. Otherwise, it would violate the vertical line test. I couldn't have a y-intercept here and another one somewhere up there, or it violates the vertical line test and it's not a function. But that takes care of the intercepts, domains, and ranges. Domains are usually easily found algebraically. Ranges, not so much. Ranges are hard to find unless you have a graph. Nah, we got a graph. Based on the graph, the domain is the set of all x values where the function is defined. It's defined looking along the x-axis, starting at this x value and running over to this x value. So it's defined from -3 to 3, including the endpoints. There's dots on the graph. So the domain of the function is -3 to 3, closed interval. The range would be the y values that come out of the function. Look over here, I see no y values, no y values. When I reach y equals 0, we get 0 out. In fact, we get it out a couple of different places. We get all of these y values out. going back and forth, looking at y equals a constant. These horizontal lines intersect the curve. Actually, if we look at 1, it intersects the curve in 4 different places. So definitely you get 1 out of this function in 4 different ways. And so forth, moving upwards between y equals 2 and y equals 3. We only get those values out twice when we look strictly greater than 2. But anyhow, we get those values out. And 3 is the biggest value that we get out of the function. So the range must be from 0 to 3, including the endpoints. The interval, the closed interval, 0, 3. So let's see, that leaves a conversation about even and oddness. How about symmetries? What kind of symmetry does this have? It's symmetric with respect to the y-axis. Think in terms of mirror images. Symmetric with respect to the y-axis, then it's an even function. It does the same thing on the left as it does on the right. This function, whatever the formula for it is, absorbs negative signs. Let's plug in, how about 3? If we plug in 3, we get out 3. Let's plug in -3. We also get out 3. This function can't tell the difference in 3 and -3. Both times it gives out +3. It can't tell the difference between -1 and 1. Both times it gives out 0. It can't tell the difference in 2 and -2. Both times it gives out, I'd have to figure out the slope of that. It gives out, well, it looks like it's about 1.5. Whatever you plug, when you plug in 2, whatever you get out, you get the same thing out when you plug in -2. It has that kind of symmetry. It absorbs negative signs. It is an even function. Suppose it could also be an odd function. It's not. F is not symmetric with respect to the origin. If it were, you've got things up here in the first quadrant would have to have corresponding points down here in the third quadrant. Remember, over and up, and you find a point on the graph for symmetry with respect to the origin, we'd have to go back and down and find a corresponding point on the graph. So whatever happens in quadrant 1, there's a symmetric thing that happens in quadrant 3, and there's nothing in quadrant 3, so it doesn't have that symmetry. Whatever happens when we go back and up into quadrant 2, the same type of thing would happen when we go forward and down, and it doesn't. There's nothing down here in quadrant 4 to have that type of symmetry with respect to the origin for the behavior in quadrant 2. Things up here have corresponding things down here. Things in quadrant 1 have corresponding things down here in quadrant 3. So it doesn't have that symmetry with respect to the origin. That being the case, by theorem 2.3.a, it's not an odd function. So there's how we can address symmetries to extract even oddness information. Let's do another one. Consider this graph. Okay, I'm going to complain a little bit about what information they're trying to convey here. They're trying to indicate that this function has a vertical asymptote along the y-axis. If you will, as x gets smaller and smaller, the graph gets closer and closer to the y-axis. It never intersects the y-axis. We need to know that because they're going to ask us about intercepts. So it never touches the y-axis. Is there implication? And I would agree with you. That's reading a lot into this little arc that they've drawn here. Also, they mean to indicate that this does not have a horizontal asymptote. It doesn't level off. It continues growing upwards. It's going to continue growing upwards slowly. For those of you in the know, this is the graph of some logarithm function. Trust me, we'll do logarithms later, but at this stage, these would be bad test questions because I have to make certain assumptions. Trust me, they mean for this to have a vertical asymptote of the y-axis. We'll address asymptotes later. And they mean that it grows without bound in this direction. So that's what they mean to indicate by this little thing here. And I will agree with you, that's reading a lot into this tiny little picture. And it's just this little arc here, and we're supposed to interpret all of that. They mean this to be a log function. But If you'll believe me on that interpretation, then x-intercepts intersects the x-axis at the point 1, 0. There you go, 1, 0. And doesn't touch the y-axis or cross the y-axis. It has it as an asymptote, as I had stated earlier. So that takes care of the intercepts. And oh, that's believing my little story about the pattern they're meaning to indicate. Domains and range, big time depends on the pattern. The domain is a set of all x values where the function is defined. So assuming the graph is extended according to the pattern we see, according to the pattern I described, x can be anything greater than 0 and anything to the right. Can't be 0 or else we'd have a y-intercept, and we don't. Remember, this is going to get close to the y-axis but not touch the y-axis. Anything to the right, the fact they've drawn an arrow in this direction, certainly I believe that anything to the right, anything strictly greater than 0 is in the domain of the function. There's some other subtle things that I have to really talk you into, and that includes properties of the range. So about the range, that'd be the set of y values. We assume here that the graph continues to go upward without bound. It could certainly look like that and have a horizontal asymptote. It could level off at some point. Trust me, and I hate to do that to you, but trust me, they mean to indicate that this grows without bound. So we will take that as an assumption of their picture. Again, this would be a bad test question. There's questions like it in the book, but that's their implication when they draw this kind of thing. What will happen when we encounter asymptotes is they'll clearly indicate what the asymptotes are. They've sort of indicated it with the presence of the y-axis, but they could do a better job. And the fact that they don't have this leveling off somewhere, I mean, it could level off at 2. It depends how it grows to the right. I need to see more of it than just this. But if it did have that kind of asymptote, they should indicate so. So granted, there's some assumptions here, but with those assumptions, that leads us to a range of -infinity to infinity. You want to take on any of these negative y values, it will. It'll do it somewhere for x positive and close to 0. You want to take on big y values, it will eventually. If this is really a log function, it's going to take it a long time to take on these big y values, but it will eventually take on those y values. So you might want to take this with a little grain of salt, but under the discussion I've given you, the range is -infinity to infinity. I like the last example better. It's a lot cleaner. No assumptions had to be made. You could see the graph of the whole function. How about symmetries? Is it symmetric with respect to the y-axis? No, there'd have to be one of those little arcs over here following along with a hand, something like that. For it to be symmetric with respect to the y-axis, there's nothing over there. It's not symmetric with respect to the y-axis. There's nothing in quadrant 2 corresponding to the points in quadrant 1. We don't have this. There's also nothing in quadrant 3 corresponding to the points in quadrant 4. But that's right there is enough to mess up the symmetry. So by theorem 2.3.a, if it ain't symmetric with respect to the y-axis, it ain't an even function. Also, it's not symmetric with respect to the origin. If we have some kind of behavior up here in the first quadrant, there needs to be a symmetric behavior down here in the third quadrant. Behavior here in the fourth quadrant has to have some kind of symmetric behavior up here in the fourth quadrant, the second quadrant. And there's none of that. There's nothing drawn over here. It does not have symmetry with respect to the origin. And so again, theorem 2.3.a, it's not an odd function either. So this function is neither even nor odd because it has neither of the desired symmetries. That I can cleanly get from the graph. The thing about the domain and range, that's a little messier for this example. In the previous one, it was fine. We saw the graph of the whole function. It didn't have to make any assumptions. Returning to the notes. Next topic is an idea of increasing and decreasing. Okay, let me try to get all of this on the little trouble getting the whole thing displayed at the same time. Start with a function f. Function f is increasing on an open interval I if for any choice of x1 and x2 in that interval, where x1 is less than x2, we have f of x1 less than f of x2. All right, let's make sense out of that verbally and visually. So this says when you plug a bigger number in, greater number, x2, you get out a greater function value. Greater values in to that function, greater values out. In terms of the picture, here's x1 and x2. x2 is greater than x1 was the story. x1 is less than x2. That means x1 is on the left, x2 is on the right. F of x1 is less than f of x2. Okay, that means f of x1 is below f of x2. Were we to go and actually plot those y values on the y-axis. So the function is greater when we put in greater x values. So I move to the right with x values. I must move up. Notice it's strict inequalities. I must move strictly up in terms of function values. So to the right implies upward in terms of y values. So the function must be doing some sort of uphill thing like this. You put in, I may call them bigger x values, you get out bigger y values. You put in more appropriately greater x values and you get out greater y values. The function must be going uphill throughout interval I, this holding for any x1 and x2 where x1 is less than x2. So it's sort of a schematic. You can imagine sliding the x1 and the x2 around just as long as the x1 stays on the left and the x2 stays on the right. Then the f of x2 value will be above the f of x1 value. And so that's what increasing means. Notice geometrically, that means the graph of the function has got to be going uphill. Well, uphill is read from left to right. We've encountered this idea before when we talked about slopes of the lines. But it's not a slope, it's something else. But the function must be going uphill when it's an increasing function. That's the informal way. I ask you to define increasing and decreasing on the test. I want a definition, not some informal thing. How about decreasing on that interval I? Well, now let's take x1 and x2, where x1 is still on the left and x2 is on the right. In other words, x1 is less than x2. This time we're requiring f of x1 to be greater than f of x2. So what happens this time when you move to the right, function values are lesser. So to the right and down is what we'll get when we trace along the function. You move to the right, function values are less. That is, the function must be going downhill if it's a decreasing function. And that's why they call them increasing and decreasing functions. Downhill, right? Yeah, when read from left to right, it's a downhill. When read from left to right, it's uphill. When read from right to left, you get it all backwards. Don't read it from right to left because the bigger numbers, the greater numbers are on the right and the greater numbers are upwards. So it's how we, by tradition, how we label the real number line. Function's constant if no matter what x is, f of x is always the same. Of course, a constant function is neither uphill nor downhill. It's nice and level, nice and flat. So there's three properties of a function: increasing, decreasing, and constant. We have arguably an algebraic way to test for increasing and decreasingness or constancy. We won't do it that way. We won't algebraically test these things. We will look at graphs and extract the information from graphs. Let's look at 26C and 28C. Okay, if you look at what we just did, we did 28A, B, and D, and we did 26A, B, and D. We skipped part C. Part C was the increasing, decreasing part. So in 26C, consider this graph again. This time, find the intervals on which the function is increasing, decreasing, or constant. Intervals, we only define this for open intervals. You might deal with this differently in Calculus 1, but in here, we're only talking about increasing and decreasing this on open intervals. So because of the way we've defined things, we'll look for where the function is going uphill when read from left to right. So let's see, reading from left to right, it's going downhill. It's going uphill here. It goes downhill. It's going uphill here. So it's going uphill on this segment of the function and this segment of the function. The function's increasing for the appropriate x values associated with this and the appropriate x values associated with that. What are the x values associated with this part of the curve? X is -1 here, x is 0 here. So anything between -1 and 0, the function's going uphill. That is, the function is increasing on the open interval -1 to 0. It's also increasing from x equals +1 to x equals 3, this segment of the curve. All right, I'm reading off x values and giving you open intervals. These are not points. Regrettably, that's the same notation we use for points. That's why I verbally explained these are open intervals, not points. It is regrettable we've got the same notation for points as we have for open intervals, parentheses, two numbers, parentheses. So this indicates the x values between -1 and 0, that is between here and here. This -1, 0 they've drawn here, that's that point, -1, 0, not this interval from -1 to 0, regrettably, but that's what the meanings are. So we're giving open intervals of x values. That's how we describe where a function is increasing. It's increasing from here to here. The x values are -1 to 0. It increases from here to here. The corresponding x values are 1 to 3, 1 to 3, that open interval of x values. In Calculus 1, the way you define increasing and decreasing, it turns out you're likely to include the endpoints. And these would actually become closed intervals. We'll follow the book that we're using and write it in terms of open intervals because that's how they've defined it. But you may see something subtly different in Calculus 1. How about decreasing? Well, it decreases from here to here. What are the corresponding x values? -3 to -1. So it's decreasing from the -3 to -1, open interval. It's also decreasing on this little part, going downhill when read from left to right. X value here is 0, x value there is 1. That's the open interval from 0 to 1. So these are the intervals on which the function is increasing, going uphill. These are the intervals on which, the open intervals on which the function is decreasing, going downhill. Don't confuse open intervals with coordinates of points. That's another reason writing words is a good thing. Written the words open interval, so you know this isn't a point, it's an open interval. It's got endpoints, but this doesn't represent coordinates of a point, it represents open intervals. Let's look at 28. All right, that thing again. Increasing, decreasing. Where's it going uphill? It looks like it's always going uphill. Read from left to right. Don't interpret this arrow here as if we were starting here and going downward. You're not. You read that's reading from right to left. Don't read from right to left. Read left to right. When I view this from left to right, it's going uphill. It's going uphill sharply and continues to go uphill. I think it goes uphill more shallowly as x values go by, but that's sort of part of the assumption that I've tried to encourage. Anyhow, it's going uphill wherever it's drawn. It's going uphill on its domain, and its domain was 0 to infinity. Wherever this function is defined on the interval 0 to infinity, the graph means to imply the function is increasing. It's going uphill when read from left to right. Back to the notes. And another topic. Okay, this increasing, decreasing stuff is useful in finding extrema of a function. Let f be a function defined on some interval I. Function f has a local maximum at c, x equals c, if there is an open interval containing c, so that for all x not equal to c in interval I, f of x is less than f of c. We call f of c a local maximum. Let's read the rest of it for local minimum. Function f has a local minimum at c, x equals c, if there's an open interval I containing c so that for all x not equal to c in I, f of x is greater than f of c. In this case, f of c is called the local minimum. Okay. What this means is, a paragraph coming up, but pretty much what this means is the function may not have its absolute lowest point at f of c, but f of c is lower, less than, well, maximums, I guess, greater than in this case. F of c may not be the absolute mountaintop, but it's the top of a mountain locally. There may be higher mountains elsewhere. That is, f of c is greater than the stuff nearby. So I'm going to interpret this, there is an open interval containing c as nearby c. So when we take x values near c, f of c is bigger than f of x. So this might represent altitude. In Johnson City, you might look to Buffalo Mountain. Around here, that's the local high point. But there's higher altitudes reached in other places. But around here, that's the local maximum in altitude. For minima, you might think, let's see, the function is less than the values around it. So that's the little bottom of a valley. So it's the lowest point in a valley. Let me keep my geographic descriptions. So nearby, function values are bigger. Now there might be smaller function values somewhere else out there, but that's the local in local minimum and local maximum. Nearby, all function values are less than a local maximum. Nearby, all functions are greater than a local minimum. And that's what the next paragraph really states. This is local behavior. Think of it as nearby behavior. So I might have a function that has a maximum at x equals 0 of 10, local maximum. But then that just means close to 0, the function values are less than 10. Out there somewhere else, function values might be much bigger than 10. So it's not a global maximum. Those are sometimes called absolute maximum. Let's look at an example. Certainly a graph will help on this. Oops. Let's go back to this one. All right, consider this graph again. Find the numbers, if any, at which f has a local maximum. What are the local maximum values? Find the numbers at which f has local minimum. What are the local minimum values? Okay, so I want to find places for local minimum first. I interchange A and B. I interchange the order on the questions. We're doing part B first, so apologies there. Let's look for local minimum. X values means that f is lesser at x than it is at nearby x values. Where does it have little bottoms of a valley? Right there and right there. Nearby, function values are bigger, and that's what matters. What open interval containing -1 would you choose? Maybe a little open interval from here to here, something like from -2 to 0. This would be the smallest function value in the interval from -2 to 0. I can't make that open interval too big. If I make it, say, from -3 to +3, that's an open interval that contains -1, but the function's not always greater than its value here. It's the same thing here, so that's too big. But nearby means I move to the left a little bit, I move to the right a little bit. In both cases, I only get function values that are greater than that local minimum. So we have a local minimum of 0, that's the value of the function, and it occurs at x equals -1. Similarly, we get the same type of behavior over here. That minimum also occurs at x equals 1. Now there's two pieces of information in this. There's where and what. Find the numbers, if any, at which we have a local minimum, and what are the local minimum values. So there's a where and a what. At which, so this is where, and this is explicitly stated as a what. What's that minimum? So the minimum is 0, that's the y values, that's the lowest point on the function, so that's the minimum, and it occurs at x equals -1, and it also occurs at x equals 1. So both of these are local minima, and maybe more than that. How about maxima? All right, for maximum, local maximums, we want the function nearby, where it's defined, to be less. Certainly that's a local maximum. The idea of a local maximum, any x value of f, nearby x values where the function is defined is how I'm going to read this. We have smaller values. So there's a local maximum associated with this point. What is the maximum? 2. 2 is the y value. Where does that maximum occur? What's the x value? X equals 0. So there is a maximum of 2 that occurs at x equals 0. Maximum there. I argue these are also local maxima. If I take an open interval containing 3 and look at function values associated with x values, granted the function is not defined on the right, but it is on the left, and this is bigger than all nearby function values. So the function also has a maximum at these 2 points. What is that maximum? The y value. Y value is 3. Where does this maximum of 3 occur? What x values? At x equals -3 and at x equals +3. The maximum is 3 and occurs at -3 and 3. More explicitly, the maximum is function value equals 3, and it occurs at input value x equals -3 and at input value x equals +3. So there's a situation of dealing with local extrema. Function may not have local extrema, as we'll see in an upcoming example. Let f be a function defined on some interval I if there is a number u in that interval I for which f of x is less than or equal to f of u for all x in the interval, that is, where the function is defined, then f is called an absolute maximum at u versus a local maximum. So what this means is no matter where you look, where the function's defined, the function never gets bigger than f of u. So it's an absolute maximum. Unlike a local maximum, where the local maximum was bigger than nearby function values. An absolute maximum is bigger than all function values. If there's a number v, where f of x is greater than or equal to f of v, right, before we had the function values less than, here we got function values greater than for all x where the function's defined, then we've got an absolute minimum. So this is the least value that the function takes on, and it's called an absolute minimum. These absolute maxes and mins are sometimes called extreme values. You know, we're going to read these extreme values off of graphs. But if you didn't have the graph, but you could find the extreme values, that might be quite useful in drawing the graph. And that's how you'll use this information in Calculus 1. Let's look at a couple more examples. The setting now is absolute extrema. Consider the graph of function f below. Notice they've given you the whole thing. It starts at 0 and ends at 5 in terms of x values. Closed interval from 0 to 5 is the domain of the function. By the way, the range is what? 0 to 4 along the x-axis. Closed interval from 0 to 4. But they want us to find the absolute maximum and absolute minimum if they exist. Identify any local max and mins. Okay, how big does the function get? Right there, highest point on the function. How low does the function go? Right there, least value of the function, lowest point on the function. Any local stuff? And these count as local as well. These are local and absolute extrema. Yeah, there's a little local minimum. Right? It reaches the little bottom of a valley, if you like, right there. And this I would count as a local maximum. Nearby, the function is lower than its value here. At 0, we get out 2 nearby where the function's defined. We get out values less than 2. You go too far away and we get out some bigger values. Well, that's why that's a local maximum and not an absolute maximum. This is an absolute maximum. The function never gets bigger than that, greater than that, never gets less than its value of 0 here. So that's the idea, and that's the verbal explanation that leads us to the conclusion. The absolute maximum of 4 occurs at x equals 4, passes through the point 4, 4. The local maximum occurs here. It is 2, and it occurs at x equals 0. Local maximum there, as described. So that takes care of their local maxes. How about the mins? Next slide. Same idea. Local minimum. Oops, sorry. Local minimum here, absolute minimum here. This is the point 5, 0. So that minimum is 0, and it occurs at x equals 5. Right? You have the value of the extrema, and you have where they occur. The value of the minimum, that's the y value. Where does it occur? That's the x value. So these come indirectly as points. They're usually described like this. The absolute minimum is 0, and it occurs at x equals 5. There's a local minimum of 1 at x equals 1, as we described earlier. That's not an absolute minimum because the function gets less than the y value here. That 1 there, that's the one that gives the y value. The function goes below that over here when you get close to 5. So not an absolute minimum. So there's some local maxes and mins. I like this one. I don't know where they got this graph, but they've given us the graph of the whole function, and I don't have to make any assumptions about this. So we can easily read off maxes and mins from this graph because they've given us the whole thing. Here's another one where they've given us the whole graph. This one's a bit more subtle. That's the reason I want to do it as an example. Consider the graph. Find absolute maxes, absolute mins if they exist. Identify any local minimum value, local minimums and local maximums. Okay, so what we've got in this graph, hopefully the video preserves this behavior. It's out of the book, so I invite you to look at the book. The book's got small images in it as well for these, but they've colored in this point here. So the graph starts here. At x equals 0, continues on through these other x values and corresponding y values. Here they've drawn a little open circle. So this function is not defined at 2. It's like the function, it's trying to pass through the point 2, 4, but it's not succeeding. It's got a hole in it at 2, 4. That's what the open circle means. What is f of 2? F of 2 is undefined because there's no point on a curve that corresponds to x equals 2. That point there, not on the curve. That's the reason they drew a little open circle. And we got the same behavior over here at the end. Open circle, function's not defined at 3. So this function, as graphed, it's not defined at 2. There's no point on the curve that corresponds to x equals 2. Again, that circle means that point's not on the curve. And there's no point corresponding to 3 on the curve. It's not there. That point's not on the curve. So there's no point on the curve corresponding to x equals 2 or x equals 3. By the way, the domain of this function would be everything, x values, that include 0 and greater than 0 until we reach 2. Doesn't include 2. Picks up after 2 and goes on to 3, but doesn't include 3. It would be square bracket 0, open bracket, parentheses at 2, union, another parentheses, picking up at 2, going on to 3, and then a parentheses at 3. That's the domain of this function. So this one is exotic. You have an informal understanding of this, but you won't have a formal understanding of the meaning until you take Calculus 1. But I don't think you'd be surprised if I'd say, this is not a continuous function. You can't draw without picking up your pencil because it got a hole in it right there. So you can't draw the whole thing without picking up your pencil. That's not a very rigorous definition of continuous, but you've probably heard it before, and it'll do for our purposes in this example. So this is not a continuous function. That's not an issue at the end point. I could draw up to 3, but the problem is the hole that's punched right there in the graph of this function. All right, so we wanted to talk about maxes and mins. Absolute minimum would be the least value of the function, no problem. There's the absolute minimum right there. We have a minimum of 1, the y value, at 0, the x value. A absolute minimum of 1 at x equals 0. 1, 3, they labeled it. That's not going to play any role in maxes or mins. I don't know why they labeled it, but anyhow, it doesn't play a role in maxes or mins. You have any local minima? Is this a local minimum? We counted it before. Yeah, but before it was colored in. This doesn't count as a local minimum. There's not a value c where the function is defined such that the function is bigger than f of c nearby. If this was shaded in, then we'd say, well, it's got a local minimum of 2 at x equals 3, but it's not shaded in. What's it look like if I magnify it a whole bunch around this point? Well, it looks a little bit like what we have here. The function, I'm hesitant to use this verbiage, but the function gets closer and closer and closer to that point, but it doesn't contain that point. It's defined arbitrarily close to that point, doesn't contain that point. Not defined at that point, it's not a local minimum. How about maximum? One might think that it has an absolute maximum of 4 at x equals 2 because of that, but it's not defined. I can't plug in 2 and get out 4. I plug in 2, I don't get anything. The function's undefined at 2. See, the graph doesn't have a point corresponding to x equals 2. They poked a hole in it there. Well, then it doesn't have an absolute maximum. The function can be made, it looks like arbitrarily close to 4, but it doesn't take on the value 4. This function doesn't have an absolute maximum. We argued previously about point 3, 2. This point's not a minimum. It's the same problem. Those points are not part of the graph. Let me try to elaborate on this a little more because this is subtle. How big does the function get? You want to say has a maximum of 4, but the function never equals 4. So what are you going to do about that? What if you pick something less than 4, like 3.9, but the function gets bigger than 3.9 because it gets really close to 4? Okay, 3.99999, but it gets bigger than that because it gets closer to 4. So it's this subtle behavior of it gets arbitrarily close to 4, but it never takes on the value 4. They've drawn it that way. You could ask a similar question. This is conceptually related. What's the smallest, least positive real number? Well, there's not a smallest positive real number. 0 is not positive, so it doesn't count. So give me a candidate smallest positive number, 0.00000001. Well, I just add another 0, or take what you've given me and cut it in half. There's not a smallest positive real number. I can get arbitrarily close to 0, but I can't use 0 because that's not positive. It's the same idea here. I can't use 4. It's not a point on the curve. I can get really close to 4, but there's not a biggest value for the function. It's a more subtle behavior than that. This you'll encounter in great depth in Calculus 1, and you'll deal with these kinds of ideas in Calculus 1, which is why I've done it now. This one's tricky, and it's tricky because of that type of behavior, getting close to 4 but not equaling 4. Back to the notes for another idea. So it takes care of absolute extrema. What went wrong in this last one? You will explain in Calculus 1. Not all functions have absolute maxes and absolute mins. They do when they're continuous. And as we observed, that last function wasn't continuous because it had a hole poked in it. I'll state it as theorem 2.3.b, the extreme value theorem. This says if f is a continuous function whose domain is the closed interval from a to b, then f has an absolute maximum and an absolute minimum. It's continuity as well as defined on a closed and bounded interval that gives you extrema, gives you absolute maxes and absolute mins. That last example, it was actually neither of these. It wasn't continuous, and it wasn't defined on a closed interval from a to b. It had a hole poked in it in the middle of its domain at x equals 2, and it didn't include the right-hand endpoint in the domain. That point at x equals 3 was excluded. So the domain wasn't right, nor was it a continuous function. So that's the reason we didn't necessarily have an absolute maximum and an absolute minimum. New topic, that of the average rate of change of a function. Let a and b be in the domain of function y equals f of x. The average rate of change of f from a to b is defined as delta y over delta x, that is f of b minus f of a over b minus a. Requiring a and b to be distinct, you never divide by 0. That will loom over your head for the rest of your mathematical life. You don't divide by 0. So we need to explicitly say that to get you in the habit. This is called a difference quotient in calculus, and probably day 1 of calculus 1, you'll look at this average rate of change difference quotient kind of stuff. And you'll do some things with it. Here, we're just going to compute these things for particular functions. It's defined to be the average rate of change. It's a change in y over change in x. When we were talking about slopes of lines, we use that same delta notation. And we had change in y over change in x. For a line, it was always the same. If it's a function who's more wiggly, then that may change as we look at different values a and b. For a line, it was the slope. Let's actually put some geometry on that, draw pictures. With y equals f of x as a function and a and b in its domain, the line containing the points a f of a and b f of b are called the secant line. What's the slope of that secant line? A picture in a second. You got 2 points on the secant line, a comma f of a and b comma f of b. How would you find the slope of the secant line? Well, you take the difference in the y values divided by the difference in the x values. That would be f of b minus f of a, divided by b minus a. So the slope of the secant line actually is this average rate of change. In terms of a picture, in blue, we've got the function y equals f of x. Here's a and b. Nobody said anything about a being less than b or anything like that. That wasn't part of the definition, but for the sake of a picture, we'll put a on the left and b on the right. On function f of x, we have the point a, f of a, that point right there, b, f of b, that point right there. If we draw the line that passes through those points, as we just defined, that's the secant line to the function for x equals a and x equals b, for these 2 corresponding points. So draw a straight line through those 2 points, assuming a and b are different. We don't get a vertical line and we don't get undefined slopes. The slope of that line, as we observe, was f of b minus f of a over b minus a. Oh, the slope of the secant line, m sub sec, slope of secant line, is the average rate of change. So average rate of change and slope of the secant line, same thing. You'll use this to talk about an instantaneous rate of change in calculus. What you'll do is you'll make a and b really close together, and that'll give you an idea of an instantaneous rate of change. Have you ever dealt with instantaneous rate of change? Yeah, that's what the speedometer on your car gives you, how fast you're going in an instant. You press down on the gas and the needle moves. You hit the brakes and the needle moves. Well, at a point in time, that's the instantaneous speed for the car, and it's changing. Well, the same thing happens here. The rate of change of this function itself changes. So it's somehow related, maybe even to accelerations. More of that in Calculus 1, but I mention it because you're going to see this stuff again, and you're going to see it in Calculus 1, especially the difference quotients. You'll see it probably on day 1. Theorem 2.3.c actually just ties together what we just said. It says the average rate of change of a function from a to b equals the slope of the secant line containing the 2 points af of a and bf of b. Not a surprise in what we just saw. Let's illustrate that with some examples. First, an algebraic example, and next, a word problem, a real-world application. Beware of ugly numbers when I say real world. Consider g of x equals x squared plus 1. Find the average rate of change from -1 to 2. If I were me, I'd write this from x equals -1 to x equals 2 and be clear that we're talking input values there, but I've copied it exactly as it's stated in the book. Secondly, find an equation of the secant line containing the point -1, g of -1, and the point 2, g of 2. Okay, that'd be 2 points on this function. And that's what we did when we found secant lines. Well, by the definition of average rate of change from a to b, we'll have that average rate of change, delta y over delta x, is g of b minus g of a over b minus a. Here, maybe we take a to be -1 and b to be 2. Substituting those in, we get the 2 and the -1 here inside the g function, the 2 and the -1 here, not inside the g function, just substituting in for a and b. What does g do to that 2? G does to x, squares it and adds 1. Okay, so we'll take the 2, square it and add 1. There's g of 2. What does g do to -1? Squares it and adds 1. So there's -1 squared plus 1. I put parentheses around the things we substituted into that function. Also put parentheses around these quantities, g of 2 and g of -1, especially this one, so I don't lose that negative sign. So we're going to have to distribute that negative sign because g of -1 itself involves some addition. 2 minus -1, okay. We'll simplify. I'm not go through every little algebraic step at this stage. 4 plus 1 is 5, right? -1 squared is 1 plus 1 is 2, 5 minus 2. 2 minus -1, that's 2 plus 1 is 3. 5 minus 2 is 3 divided by 3. That average rate of change from -1 to 2 is 1. So average rate of change is 1. Now what's that tell you about the secant line? It's got slope 1. Remember, average rate of change equals the slope of the secant line. In part B, they want us to find, excuse me, find an equation of the secant line. We know its slope is 1, and we know a point on it. Actually, we know a couple of points on it, either this one or that one. Theorem 2.3.c tells us the secant line has a slope equal to the average rate of change, and the average rate of change is 1. Let's use a point slope formula. We got the slope. We got a point. Yeah, let's use this point, -1, g of -1. So we'll plug that in. x1, y1. So -1 here, g of -1 there. Substituting in 1 for the slope. So we get y minus g of -1 equals 1, the slope, times x minus -1. There it is. The x coordinate of the point we're using. So y coordinate of the point we're using, x coordinate of the point we're using, y coordinate, x coordinate. What is g of -1? Might be -1 squared plus 1. We actually did it up here. We found out it was 2, I think. So this will simplify down to 2, guaranteed. Right-hand side, we've got 1 times x minus -1. That's x plus 1. So we get x plus 1 on the right-hand side. This simplifies down to 2, as predicted, and as happened earlier, right there, we got, right there, we got the 2 out. So we get y minus 2 equals x plus 1. Let's write that in y equals mx plus b form. I would make that part of the instructions if I had the power, but like I said, I just copied the question out of the book. Let's take the 2 to the other side. It becomes positive and we get y equals x plus 3. Does this have the correct slope? Yeah, it's in y equals mx plus b form. The coefficient of x is a slope. Coefficient of x is 1, slope is 1, supposed to be. When I plug in one of these points, -1, g of -1, do I actually get that satisfied? Actually, let's plug in 2g of 2 to double check. We haven't used that in the formula explicitly. It's implicitly in there when we used it to find the slope. But what is 2g of 2? We found g of 2 was 5. So 0.2 comma 5, we've already computed g of 2 right there, produce 5. When you plug in 2 for x, do you get 5 for y? You plug in 2 for x, you get 2 plus 3 is 5. It works. So just double checking it at the end, we did it right. So there's some illustrations of average rate of change in secant lines and a tiny little reviewing of point slope form of a line. Another example, they've given us real numbers here. So this will be a little sloppy, but I feel obligated to work some sloppy ones for you. I certainly wouldn't put sloppy ones on the test. I give you pretty clean numbers on the test, not letting you use a calculator on the test. So clean numbers are guaranteed on the test. But real data gives us that the size of the total debt owed by the United States federal government continues to grow. In fact, according to the Department of Treasury, the debt per person living in the United States is approximately $53,000 or over $140,000 per U.S. household. The following data represents the U.S. debt in billions of dollars for the years 2001 to 2013. Since the debt, D, depends on the year Y, and each input corresponds to exactly one output, the debt's a function of the year Y. Debt D is a function of year Y. We'll represent it as D of Y. You might feel at this stage a little uncomfortable about using Y as the input for a function. We usually had Y equals f of x. They're just letters, and this is how they're using them, and probably intentionally thrusting this Y as the input value on you just to give you the experience of that. So don't get hung up on Y equals f of x. There's more to algebra than x's and y's. Here we've got d's and y's is the inputs, d's is the outputs. So here's a graph of year and debt, not clean numbers. We'll come back and look at this chart if we need to. We're gonna plot all these points. I might ask you, trust me when I make a graph of these, but they're gonna ask us to plot, ultimately to plot all the points, but to plot a couple of points, and so on. They ask us to plot all the points in the Cartesian plane. We'll do that. Then they ask us to do some things with average rates of change in lines. Draw a line segment from the point 2001 and national debt to 2006 national debt. What does the slope of this line segment represent? Find the average rate of change of debt from 2002 to 2004. Find the average rate of change of debt from 2006 to 2008. Find the average rate of change from debt from 2010 to 2012. What appears to be happening to the average rate of change? So we're looking for pattern. So we'll have to repeat all of this. First, graph all those points. So we're about to graph these. We'll have the y-axis, the horizontal axis, the abscissa, if you remember that word, ranges from 2001 to 2013. So we'll calibrate that axis accordingly. The debt ranges from, so it continues to go up, so 5,807 to 16,738. So we'll keep that in mind when we calibrate the d-axis or the ordinate. All right. So for a graph, we get something like this, expressing y here, letting it range, say, from 2000 to 2015. That encompasses all those years. Here's the debt. To get a clean scale, I had to kind of let it run off the top. but we'll do a scale something like this. These points I have plotted by hand. It's real data. They kind of wiggle around a little bit like that. All right. There's the points plotted. In part B, they say draw a line segment from the point 2001 y value to 2006 y value. So 2001, 2, 3, 4, 5, 6. A line segment joining these 2 points. What does the slope of this line segment represent? That's a secant line to the curve, ain't it? When the curve, I don't know, who knows what the curve is precisely. We're doing more a statistical approach to this, but we're finding the average rate of change between 2001 and 2006. The slope of a secant line is the average rate of change. They ask us to draw the line segment. They didn't ask us to do any computations. They do later. But draw the line segment. What does it represent? It's the slope of a secant line, so it represents the average rate of change of debt from 2001 to 2006. What do the units be? I think it's probably billions of dollars per year would be the units if we were to compute that slope. So secant lines represent average rates of change. That's a secant line. Its slope represents an average rate of change. Find the average rate of change of the debt from 2002 to 2004. Do it also from 2006 to 2008, another year. So we'll have to go back and grab those relevant points from the table. In 2002, we had the point, 2002 for the year, $6,228 billion for the Y, for the D coordinate, the output. 2004, we had an output of 7,379 billions of dollars. So we want the slope. That would be change in output divided by change in input. I mean, you're used to seeing it as delta Y over delta X because Y was the output and X was the input. Okay, jumble the letters around. The output is debt, capital D, so we'll have that, changing that in the numerator. Year was the input, represented with a Y, we'll have that for the input. Output change divided by input change. Line these up. If we use this for the, what would I call this? Y sub 2, D sub 2, using the subscripts, Y sub 1, D sub 1, if I go back to the formula for slope. But you know, it's a change in D divided by a change in X. So if we take this minus that, for the change in D values, we need to take this minus that for change in Y values. Do the correspondence. These form a point. You see the 7,379 in a similar location as the 2004, as we've discussed in the past. So take the difference in D values divided by the difference in Y values. That produces, when you do the arithmetic, 575.5. The units were billions of dollars for the Ds, and Y was a measurement in years. So I think I stated this earlier. What we get for units here is billions of dollars per year. Average rate of change, that's the average rate of change from 2002 to 2004. So it's 575.5. 2006 to 2008. Okay, we need the 2 points associated with those years. We'll do the same computation. Same idea, this minus that, 10,200 minus 8,500 over this minus that, 2008 minus 2006. This time it produces, upon simplifying, calculator if you like, 759 billions of dollars per year. So it went over this time period from 575.5 up to 759. Next, they're going to ask us to do the same thing for another time period. 2010 to 2012. Okay, we need the 2 points that correspond to those years. There they are. Do the same thing. Difference in D values divided by difference in Y values. This time it produces 1,252 billions of dollars per year. What was the trend? This thing's going up. This average rate of change is going up. Let's go back to the previous slide. We had 575.5, 759, 1,252. It's going up. What appears to be happening to the average rate of change as time passes? The average rate of change is increasing as time passes. So that's my answer to that. So we're talking about the rate of change of a rate of change. The average rate of change itself is changing. You'll see this related in Calculus 1 to something called derivatives. If we were to speak of not dollars in time, but maybe distance in time, and express velocities as something like miles per hour, or speeds as miles per hour, that'd be a rate of change of position. What's the rate of change of velocity? The rate of change of the rate of change? Acceleration? So this is somehow related to an idea of acceleration. It's an accelerating national debt, I guess is how we describe it. And if we go back and look at the graph originally, you'll see it's getting steeper and steeper. The average rate of change is getting steeper and steeper. Going back to the graph, a certain steepness here, another steepness there, and maybe a greater steepness here. They were doing this, I think, over 2-year periods in the numbers we computed. The denominator was always 2 years, I think it was. But we see the curve getting steeper, and that's reflective of the fact that this represents an accelerating process. And that's the last example from this section that takes care of properties of functions. What we'll do in the next section is called a library of functions. So you're not going to be a real excellent grapher at the end of pre-calculus. You will be after calculus 1. Well, you'll be as good as anybody else, at least. But you will be good at graphing certain functions, the functions in the library of functions. So we'll set up a special class of functions that you are good at graphing now, and we'll add to that library later. We'll add logarithm functions and exponential functions in chapter 5. So back really to graphing and techniques of graphing. The next 2 sections are related really to techniques of graphing. So I'll see you in those sections here shortly. Have a nice day.